Thanks everyone for showing up remotely for my talk. So yeah, as Roland said, the title is short-range correlation physics in low-resolution pictures. And namely, what I'm going to try to do is use RG methods to reconcile two very different pictures of nuclei that have emerged in recent years. And I should point out from the beginning, these are my collaborators, and the people in red are highlighted because, as usual, they're the young people who did all the work. Okay, so before we begin, let me just define the basic terms. So what do I mean by low and high resolution scale pictures? So let me remind you that any model Hamiltonian comes with an implicit resolution scale. You can think of it, if you like, as an ultraviolet cutoff, or maybe more generally, you can think of it as something that imparts maximum momenta that you'll find in low energy wave functions. And I'll use this symbol lambda to denote this resolution scale. Yeah, so let's start off with just a cartoon of what we mean by a high resolution picture. So this is a Hamiltonian with a very large cutoff. And so you can imagine taking a snapshot of the nucleus, and you'll see things like this, where you might find isolated pairs with very large back-to-back momentum that have been kicked up due to the strong two-body interaction. And if you look at things like momentum distributions, you'll see things like a long, slowly decaying tail well above the Fermi momenta. Okay, so high resolution pictures, we have correlated pairs with large back-to-back momenta, and high momentum tails are everywhere. For the low resolution picture, we have a cartoon like what's shown here. And this is something where our theory resembles something that looks like a mean field picture. And what that means in practice is there are no high momentum tails. And so if you were to look at something like the single particle momentum distribution in a many-body system, you would find that the strength rapidly dies off if you go much above KF. Okay. So let me just tick off some examples of both of these low and high resolution theories. So let's start with the low resolution pictures. So one example that everyone here is familiar with is the nuclear shell model. Another example is anything that's based on nuclear density functional theories. So both of these phenomenological approaches, which are really the backbone of nuclear structure theory, they all kind of have at their base this picture of in zeroth order, the nucleons are moving in relatively independent particle motion with maybe some weak residual interactions, which can kick you out of the Fermi sea. And the point here is that pretty much all of our nuclear structure, with emphasis on structure, models are what I would call low resolution pictures. Okay, so what about the high resolution scale pictures? Let's give some basic history there just to see how people came up with this view of the nucleus. So how did the high resolution picture arise? So in my mind, there are really two thrusts of work in the 50s and 60s, which kind of revealed this picture. So the first example was the early analyses of NN scattering in the 50s and 60s. And basically what they found was that in the S wave phase shifts, you have this change of sign at these intermediate energies that signifies you going from attraction to repulsion. And the point here is that if and this is a big caveat here, if you insist on using a local form for the potential, so that it's diagonal in coordinate space, then in order to describe such a sign change in the phase shifts, you're forced to implement a strong short-range repulsive core. And so based on those early analyses, the usual kind of textbook cartoon of the nucleon-nucleon interaction was deduced. Okay, and of course, if you, so for our purposes, it's maybe a little more useful to think in terms of momentum space. So if you look at that picture of an interaction with the strong short-range repulsive core and go to momentum space, as you know, that results in a very strong mixing of momentum modes over a wide range of scales. So this is a heat map plot of the argon V18 potential in one of the S waves, I believe. And you can see that it couples up pretty high in momentum. And let me just remind you that in a typical nucleus, the typical Fermi momentum lives down here somewhere. So you have a coupling of strength to momentum modes that are well above the typical scales in a nucleus. So the second kind of historical development that led to this picture of the high resolution view of nuclear forces came about in this very nice 1955 paper by Bogner, Eden, and Francis. And basically what they did was they analyzed 5 different medium high energy experiments, trying to see if they could reproduce it using the prevailing low resolution shell model type picture that existed at the time. And basically what they found was that they're completely unable to describe these medium and high energy, hard momentum transfer processes unless they build into their model a correlation such that the one body momentum distribution has a long tail that extends well beyond that of an independent particle model. And so here's a nice quote directly from the paper, basically saying that at least if you look at these types of hard processes, the usual assumptions of the shell model are insufficient to describe the data. And one thing I want to point out, because it will appear subsequently when I discuss modern short-range correlation phenomenology, is it's very interesting. And in this paper from now like 70 years ago, Bogner already identified basically the key configurations to make his analysis work. And these are the configurations that in modern lingo we would call short-range correlation pairs. And so in Bogner's analysis, he realized that to describe such a high momentum tail, to describe these 5 different reactions that he studied, the important configurations in the nucleus were like the cartoon shown here. And namely, the thing that really makes it go is when you have 2 nucleons which have been kicked up to relatively high relative momentum, small center of mass momentum. And in that limit, he argued, just using physical grounds, that the many-body wave function, oops, sorry, I'm using my iPad, which I'm not used to. A number of blunders here. But the key observation that he made was that the many-body wave function in this limit should approximately factorize. And so you've got a piece which depends on the correlated short-range pair, and then a piece which is relatively soft and low momentum in nature and dominated by mean field physics. And even though he didn't call it this in that paper, this is really a short-range correlation. And moreover, this factorized wave function ansatz that he identified on physical grounds really is the basis of a lot of the theoretical phenomenology that's used to analyze modern SRC experiments. Okay, so that's just kind of a broad brush intro to how the high resolution pictures of nuclear interactions came about. Now let's circle back to low resolution theories. And to kind of motivate that, let's look at a plot that a lot of you have probably seen now, thanks to Heiko Hergert, that shows the impressive progress that's been made in ab-initio calculations of medium mass nuclei, thanks in large part to the influx of these low resolution nuclear Hamiltonians. So here's the state of the field in 2005. Back in the day when people were using predominantly these high resolution, very high momentum, hard 2- and 3-body interactions. And not surprisingly, you're really limited to the lightest of the nuclei that you can calculate. And then here's a nice plot from Gautahagen that shows the progress year by year using these high resolution interactions. And the point is that these methods are so hard, or these interactions are so hard, you're pretty much forced to use exact methods like quantum Monte Carlo that scale, exponentially or factorially with system size. And so the point then is that due to Moore's law and the fact that you're forced to use methods which have exponential cost as you increase the size of your calculation, you have this slow, flat, linear trend year by year. And if this were to hold true, if we were to never use these low resolution nuclear Hamiltonians, we probably wouldn't hit calcium 40 calculations until 2040. Okay, so it kind of makes a big difference. And as everyone here probably knows, the situation is much more optimistic than that. Again, thanks to these low resolution Hamiltonians that are in vogue right now. And here's another plot that Heiko made, already somewhat out of date, but it gets the message across that the territory in the nuclear chart that can be calculated using ab-initio methods has really exploded dramatically. And another plot which shows this, again, from Gautahagen's APS talk, showing the year-by-year progress. And you see that, roughly around 2010 is precisely when these soft, low-resolution interactions really started to be used in a widespread manner. And you see this dramatic explosion, this hockey stick behavior there. And the point here is that, why is that? The main takeaway point here is that the use of these low resolution interactions, whether they're from chiral EFT or interactions which have been further softened using various types of RG transformations, all of these low resolution interactions basically allow you to make use of polynomially scaling many body methods. And things like coupled cluster, IMSRG, even many body perturbation theory becomes quantitatively reasonable. And so, so that's kind of the main reason why you've seen such an explosive growth in ab-initio nuclear structure theory in the last decade or so. Okay, so since the point of my talk is to try to understand how you can reconcile or connect the high resolution picture of nuclear physics, which derives from SRC studies in hard electron scattering experiments, with the conventional low resolution picture, which dominates nuclear structure theory. I'd now like to take a few minutes to just give a very broad brush overview of some of the modern high resolution short range correlation phenomenology. So the main development here stemmed from a series of experiments from the early 2000s and still ongoing, done mostly at places like Brookhaven and JLab. And the idea here is that they design these double knockout experiments where you knock out short-range correlated two-nucleon pair. And the main advance here is that besides the usual inclusive type measurements, you do more exclusive measurements where you detect both knocked out nucleons and then reconstruct the initial state. And so the main breakthrough here is that they're able to really cleanly isolate the mechanism that leads to these ejected SRC pairs. And they do this by very carefully choosing kinematics to minimize or eliminate any ambiguities that would arise from things like meson exchange currents, final state interactions, and so on. And kind of the 20,000 foot in the air executive summary of these 20 years of measurements is that in their interpretation of these measurements, which again are all done in this high resolution view, the main takeaway points are really these two things here. So namely that there are two distinct regions of nucleon momenta in the nucleus. So you've got mean field-like nucleons and then these hard SRC correlated pairs, which are responsible for these long fat tails. And based on their analyses of all these experiments, a consensus has seemed to emerge that roughly 20% of nucleons in the nucleus are in SRC pairs. 70% of the kinetic energy stems from these SRC pairs and so on. So I'd like to now just kind of tick off some of the more specific SRC phenomenology, because I want to then circle back later and try to understand how we can reproduce this or interpret this in a low resolution framework. Okay. So the first thing is the fact that when you do these inclusive quasi-elastic cross-section ratios, what you find is that you get, for a region of Bjorken X, you find these plateau behaviors, okay? And the standard way, so yeah, this is what's being plotted, is this ratio of the A-body inclusive cross-section over the deuteron scaled by the particle number. And so the way that this is interpreted in the standard high-resolution SRC view of it is that this vertex here, where the knockout is happening, if you look at it with a magnifying glass, what's going on is that due to these hard scatterings, due to the high resolution nucleon-nucleon interaction, you're kicking guys up into high states above the Fermi level, and then a photon's coming in and it's hitting it and blowing it apart and knocking it out. And within this picture, within this interpretation, they're able to relate this ratio of cross sections to a ratio of the high momentum tails of the momentum distributions in the A-body system over the deuteron. Okay. And from this, they conclude that the plateaus in the Bjorken X imply that all nuclei should have roughly the same shape of their high momentum tails in their momentum distributions. And that's indeed borne out in these nice calculations by Bob Varinga et al. And moreover, the relative height of these plateaus here is interpreted as the relative probability of finding a two-nucleon SRC. Okay. Okay, so the second kind of key bit of SRC phenomenology in the standard view is to understand the kinematics of the knocked out nucleons. So again, dating back to Bruckner's work, this is kind of the cartoon of what a SRC pair is, large, almost back-to-back momenta. And so because of that, when you look at the knocked out pair, you should find that they fly out mostly back-to-back or almost back-to-back. And moreover, that these will be dominated by relative S-wave pairs. The other kind of phenomenology of these reactions is that the distribution of the pair center of mass momentum is really a soft, low momentum quantity. It's kind of like a mean field quantity. And it's well described as a Gaussian, where the characteristic width is something on the order of the Fermi momentum. Okay, so those are the main features of the kinematics of these reactions. The other crucial thing is that there's this so-called NP dominance at intermediate ranges of relative pair momentum in this range here. And so the idea here is that if the part of the nuclear force which was responsible for kicking these guys up above the Fermi surface, if that was a portion of the interaction which acts equally on NN, NP, PP, and so on, then the number of pairs of SRC pairs of each species would be roughly given just by what you would estimate by counting pairs of each type. But what's actually found, again, in this range of momenta, is that you have a great enhancement of neutron-proton pairs over the others. And roughly 20% of the nucleons in a nucleus are SRC pairs, but the vast majority are neutron-proton. And of course, this is interpreted as arising from the tensor force. So the tensor force, in the 3s1 channel only acts on NP pairs. And so therefore, this is well understood in that picture, why you have this NP dominance at this intermediate momentum scales. So the fourth bit of phenomenology that we'll try to understand later is that there's also eventually a transition from this NP dominance to what the practitioners call scalar counting at higher relative momentum. And the idea here is by looking at these cross-section ratios of double knockout to single knockout, they're able to interpret that in terms of the pair fraction in these SRC pairs. And what's found is that, in these intermediate regions, you have this huge enhancement of the NP pairs over everything else due to the tensor force. But as you go up further in momentum, the values kind of relax to what you would get from this naive counting pairs argument. And so the way this is interpreted is that in this limit, you're no longer probing the tensor force, but really you're probing the repulsive core, which, as I said earlier, acts the same on the different pairs of nucleons that you can have. Okay. And so this just agrees what you would get from counting. Okay. Yeah. And then kind of the other bit of standard SRC phenomenology is this notion that protons speed up in neutron-rich nuclei, at least in this intermediate range of momenta where the tensor force is dominating. Again, the idea is that so you have an equal number of neutrons and protons that are kicked up above the Fermi level. And so therefore, as you go to more and more neutron-rich systems, a higher fraction of the protons are knocked up above the Fermi level. So this is why it's often stated in these papers that protons speed up in neutron-rich nuclei. And here is an example of an experimental analysis. I forgot to put the reference there, but it's, oh yeah, no, there it is. It's from this 2018 Nature paper. And you see that indeed the minority species, in this case, the protons, their correlation probability grows, and it has this nice linear n over z dependence. And so if you interpret this in terms of momentum distributions, you have this picture here where for n greater than 0, a larger fraction of your protons are kicked up above the Fermi level. And finally, the last bit of kind of modern SRC phenomenology is maybe the key theoretical tool in their toolbox. It's something called the generalized contact formalism. So this is a very nice series of works originally by Ronan Weiss and Nir Barnea and collaborators. And I'll show some results here from this more recent paper. The basic idea of the GCF, even though they motivate it by drawing on work done by Sheena Tan in the description of cold Fermi gases with large scattering lengths. But you could say that really the key assumptions here of this GCF method are really the same ones that are laid out in this 1955 paper, Bogner, namely the fact that you've got this factorization of the many-body wave function in the limit of whenever you've got a pair getting really close to each other in coordinate space, or if you think in momentum space, the pair has large back-to-back momentum. So in either one of those cases, the many-body wave function factorizes. And the key thing here is that this blue piece is universal. It's the same for all nuclei. It's fixed by the two-body Schrödinger equation. And this red piece encodes all of the complicated many-body dynamics. And so this picture is used to explain things like universality in the pair density distributions at short distances. So, for example, if you look at the relative pair density in various two nucleon channels labeled by this alpha, you find that if you do it for a bunch of different nuclei and then rescale them so that they all fall on top of each other at r equal 1 Fermi, you find that they all have exactly the same shape at short distances. And so the way this is interpreted in this GCF framework is that using this wave function factorization, which underlies everything, you can show that these two-body pair distributions and pair momentum distributions factorize. And so these terms circled in red are related to these chi functions here. And they basically encode all the A-dependent many-body dynamics, and they're referred to as the nuclear contacts. And then the terms in blue explain why all these quantities have universal shapes for all nuclei. But of course, they're not the same for different NN potential models, as you can see from these 4 panels here. And that's just reflecting the fact that these functions here, even though they're universal, the same for all nuclei, they'll be different if you use a different force model. Okay. And so the point of this analysis, which you can get a lot of mileage out of, is that if you look at things like ratios, which are predominant, for example, in the analysis of these inclusive scattering measurements, you find that all the scale and scheme dependent parts in blue cancel out, and what's left really is approximately scale independent. So it doesn't really depend very strongly on what force model you're using. And so the way they interpret that is that these ratios of these contacts are really only probing mean field physics, okay, or low momentum physics. And so we'll try to understand that in RG language in a bit. And here's an example illustrating that. So the point is that even though these so-called nuclear contacts themselves are not scale and scheme independent, their ratios are. And here's a plot from this earlier paper, which shows that for a number of different interactions, for a number of different NN channels and a number of different nuclei, and you see that indeed they're all clustered together. So there's very weak scale and scheme dependence. So that's evidence that you're really only probing low momentum physics in these things. Okay, so that was kind of a lightning recap of SRC phenomenology. So now how do we interpret this or reconcile it with the low resolution picture that dominates nuclear structure theory? And so the key thing here is we're going to rely on RG techniques to continuously vary the resolution from a high resolution picture to a low resolution picture without changing the actual observable physics. And in the process, we'll be able to see how interpretations and relative contributions of different components, how they get shuffled up as you vary the resolution scale. So one slide on the RG. So there are basically two schemes that are widely used in low energy nuclear physics. The first one is really analogous to the original Wilsonian RG, where you are literally integrating out momentum modes above some floating cutoff and lowering that cutoff. And the downfall of that is you only preserve physics up to the scale of degrees of freedom that you've kept. More powerful for our work is something called similarity renormalization group, which you can kind of view as a unitary version of RG ideas. And the cartoon here is that under SRG transformations, you're driving a Hamiltonian progressively more and more towards the diagonal. So this parameter lambda kind of parameterizes how clustered to the diagonal you are. Okay, and so the claim is, even though that these two approaches look rather different, the main takeaway point that we'll make use of is that if you're looking at low energy states, then this lambda parameter basically plays the same role as this uppercase lambda parameter in the Wilsonian RG. Namely, for low energy states, momentum modes much higher than this lowercase lambda are highly suppressed. Okay, so the basic thing that we're going to do here, the game plan, is we're going to take a look at some matrix element which might enter into one of these hard electron scattering processes, which is schematically shown down here. And we're going to basically just insert unity using our unitary RG transformations. And we're going to map it from a theory at a high resolution picture to a theory at a low resolution picture here. And so you see the process of doing that mixes up and entangles what was previously called reaction, what was previously called structure. As you change the resolution scale, everything gets mixed up here. Okay. Yeah, so there's kind of a nice analogy where we ultimately want to go with this nice analogy with what's done in high energy QCD, where when you look at hard scattering processes, you make analogous factorization, and this factorization scale is not unique, but nevertheless, the observable form factor is independent of how you choose the factorization scale. And then things like parton distributions, you can extract at a given scale, but it's process independent, and so it can be used elsewhere. Meanwhile, the short distance piece can be calculated in perturbative QCD. In low energy nuclear structure, kind of the analogous factorization is shown up here. So these spectroscopic factors kind of play the role of parton distributions, and the single particle reaction cross sections play the analogous role of the perturbative QCD part of the calculation, for the reaction part. And so that leads to a number of open questions. So as you vary this resolution scale, what's the scale and scheme dependence of things that you extract? Are some scales and schemes easier to extract things than others? Same thing with interpretations. And the most important thing to understand this is, what is the structure of these evolved high momentum operators under the RG? And so to explain that, I just have kind of a simple qualitative hand-waving argument here to dissect the form of these RG evolved operators, focusing on operators which probe high momentum modes in the high resolution theory. So let's start off by looking at two-body wave functions, and let's look at the low momentum components of low energy states. And the first thing we notice, so here's a plot showing the momentum distribution calculated for several different interactions at different resolution scales. And you see that at low momentum, everything pretty much falls on top of each other. So this is just reflecting the fact that the RG preserves the long distance or low momentum structure of the theory that you started with. And so you have relationships like this, where P denotes a generic soft momentum. Okay. What about high momentum components of low energy wave functions? Here you can make use of some very simple scale separation arguments. So let's say we're looking at low energy and high momentum, where low and high are defined with respect to this RG scale lambda. You can show that the high momentum components of the high resolution theory wave function obey these types of factorized contributions, where the key thing is the terms in blue encode all the hard state independent high momentum physics, and the terms in red are low momentum objects, and they encode all of the state dependence. So this is really analogous to the operator product expansion applied to a non-relativistic system. So, yeah. And so you can make use of this construction to see how your operators evolve as you vary the resolution scale. So here's a schematic, again, just doing the simple two-body system for simplicity, where we break the momentum ranges into soft and hard, as indicated by lambda and lambda naught. And so now we simply make use of the things that I showed on the previous two slides. We make use of this leading order factorization formula. So you're basically doing an OPE for the wave functions. We use that the IR structure is unaltered under the RG. And then we make use of scale separation. So Q generically denotes a hard momentum, P generically denotes a soft momentum. Okay. And so if you go ahead and do a couple lines of algebra, you're able to match the matrix elements for the high resolution theory to the low resolution theory, and you get these nice factorized forms here. And the key thing here is that this term in blue is state independent. It entirely depends on hard momentum physics, and it depends on the operator in question that you started with. In contrast, this term in red only involves soft momentum physics. It's the same for all high momentum operators, and it carries or encodes all of the state dependence. Okay. And just to kind of fill it in, what these things are, here would be the form of this Wilson coefficient as a convolution of these different high momentum functions and integrations over various slices of momentum space. And so you can show generically that the form of some RG evolved operator is given in this form here. So you have the original operator at the high scale with some wave function renormalization, and then you've got some sequence of local operators where these Wilson coefficients, again, encode all the high momentum physics that you're integrating out. Okay. And so you can then ask, well, what about an operator that probes high momentum components in the initial high resolution theory? What does it look like in a low momentum theory where there are no explicit high momentum modes? And so we can look at this. And so we just go ahead and use the expressions on the previous page and take matrix elements. And so we're looking at an operator, an initial operator where we assume that it only is sensitive to high momentum modes. Since the RG evolved state is soft, this is suppressed or zero. And so therefore the leading contribution is from this first Wilson coefficient. And so if you apply this, for example, to the momentum distribution for Q much greater than your RG scale, your soft RG scale, you find that the momentum distribution has this nice factorized form where all the Q dependence is out front and it's state independent, and all the state dependence only depends on soft physics, low momentum physics. Okay, so this is all very schematic, done for the two-body wave functions. I claim you can generalize this to arbitrary A-body states. This was done already almost 10 years ago in this paper with Dietrich Roscher. And then Anthony Tropiano, Fernstall, and myself are currently filling in some of the details in a paper that's in progress. And so if you look at things a little more explicitly, oops, this should be lambda not. What you find, for example, the momentum distribution now in a mini-body system has the same factorized form. If you look at another example of an operator which probes high momentum, oh shit. If you look at another example, like the static structure factor, which is just the Fourier of the density-density correlator, you find that it likewise obeys a similar factorization into hard and soft physics. And this factorization is completely generic. So the hard physics in blue is universal. It's state independent. It does depend on what operator probe you're looking at, and it's fixed from few body physics. Whereas the stuff in red is soft. It only involves low momentum physics. It's the same for all high momentum probes, high momentum operators. And it carries all the A dependence of your problem. Okay. And so the point here is that this RG evolution of these high momentum operators provides a very clean link between few and A body systems. If you like, it effectively derives the GCF. It explains why you often find correlations and scaling relations between two different observables if they both probe high momentum physics because they have the same leading OPE. And moreover, you can, in principle, look at things like the subleading OPE contributions to actually calculate deviations from scaling, at least in principle, although we haven't done that. So let's real quickly recap the SRC phenomenology in this low resolution picture. So let's look at the first one, this fact that the inclusive cross-section ratios and these plateaus in Bjork and X imply that the high momentum tails of momentum distribution should be universal in different nuclei. And again, this follows rather trivially in our approach. So this is the form of the evolved low resolution operator taken in an evolved low resolution state. And you see that sure enough, all the Q dependence gets factorized out front. And then what remains here is a soft matrix element, which encodes all of the A-dependent rescalings of these plateaus. Yeah, and so yes, this is why you get the plateaus. You take the ratios and the gamma of Q cancels out, and what remains is independent of Q, at least to leading order in the OPE. Okay, so the point here is that this really probes low momentum mean field physics, at least to this leading order of the OPE that we're doing. It's scale and scheme independent. And this really completely confirms what has been confirmed in the SRC literature using this GCF method about these ratios of inclusive cross sections, namely that they don't really probe anything other than soft mean field physics. Okay, what about the other bit of phenomenology, namely that most SRC pairs fly out almost back to back in relative S-wave pairs, and that the extracted pair center mass momentum distribution is nice and soft. It's a Gaussian with the characteristic size of KF. How do we see that in our approach? Well, again, you go to the leading form of the RG evolved operator with the leading form of the OPE. And this is the generic form that we have here, where this alpha just kind of is a shorthand for what NN channel you're looking at. And so this is the form for the pair momentum distribution, which enters in the analyses of these experiments. And the point here is that this involves a matrix element of a smeared contact operator. And therefore, we immediately see that for high relative momentum pairs, they have to be dominated by relative S-wave states because that's the leading term in the OPE. Moreover, we see that since these wave functions down here at the end, these are soft RG evolved wave functions. So they're dominated by mean field theory configurations, very weak high momentum contributions. So what that means then is that the center of mass Q distribution necessarily is given by mean field physics, and it's going to be smooth and probably Gaussian with a width that's set by the Fermi momentum. Okay, what about this NP dominance at intermediate relative momenta, and then the transition to scalar counting at higher momentum as you move from the tensor force to the repulsive core? So again, in the low resolution picture, it's actually simpler to see this because the mini-body calculation is completely irrelevant. All the Q dependence gets factorized into the Wilson coefficient, which is given by two-body physics. And so you can already see this transition just by looking at the ratio of the Wilson coefficients for the evolved operators in the 3s1 channel and the 1s0 channel, since those are the dominant ones which enter. So 3s1 dominates here, and then it transitions to 1s0 down there. And so you see this already from this ratio of Wilson coefficients, and you see, sure enough, in exactly the range where the tensor correlations dominate, you see this big spike in this ratio, but then as you go to higher and higher momentum, things relax to roughly the same magnitude. And what about the GCF? So just a reminder that the main object in this GCF, well, besides these two-body wave functions, it's these so-called nuclear contact coefficients. And the point is made in this literature that when you take ratios, the scale and scheme dependent pieces cancel out. And so what's left is a ratio of these contacts in different nuclei. And there, what you find when you do this is that these ratios are indeed, to a good approximation, scale and scheme independent, even though the contacts themselves are not necessarily scale and scheme dependent. And so how can you understand that? Oops, what happened here? This is why you shouldn't give a talk on an iPad for the first time for a live seminar. Okay. Try to ignore those handwritten circles and that circle with an X through it. So the point I'm trying to make in this slide here is that these contacts can be written as a matrix element of this 4-fermion operator. And so what's shown on the left here is the form it would take in the high resolution theory. Now do an RG transformation where you evolve lambda to very small values. You find that this nuclear contact is not RG invariant. It picks up some overall multiplicative factor, which depends on the RG scale that you're evolving it to. But the point here is that it's A independent. And so therefore, when you take ratios in different A, this term cancels out in the ratio. And so therefore, you arrive at the conclusion that the ratio of contacts taken in different nuclei is approximately scale and scheme independent, just from these simple leading order RG arguments. Okay, there's no way in hell I'm going to have enough time to talk about this. This is older material, but I figured since at least the MSU people haven't seen this, it would be nice to show it. Basically, just the quick summary of it is that we looked at kind of the simplest knockout reaction you can do, and that is deuteron electrodisintegration. And we play this game where we perform RG evolution on the wave functions and the transition operator and see what happens. And kind of the takeaway point here is that things such as final state interactions, those are strongly scale and scheme dependent. So here's one example, which I'll just show without really explaining it. So this is an example taken at kinematics, which would be relevant for SRC studies. And what's shown is a series of calculations. So the term in green is the exact result. The term in the dashed black is what happens if in the high resolution theory, you try to ignore final state interactions. And of course, it's a disaster there. But then the cyan and the blue show what happened if in the RG evolve theory, if you ignore the final state interactions. And there you see that the import of final state interactions is very minimal there. So that might be something to explore. The folklore has always been that, shouldn't hard processes be very complicated or non-intuitive to describe in a low resolution picture. But maybe given this factorization behavior of all the Q dependence and the fact that we can find certain parts of regions of kinematics where the final state interactions are strongly scale dependent, maybe it's something worth revisiting. And I'm going to skip the rest. It's too bad I don't have time to do that. But let me just flash up my summary page. So hopefully I convinced you that there really is no contradiction between these low and high resolution pictures of the nucleus. The point is that modern RG methods give you a tool to smoothly connect one from the other. In that sense, there is no absolute or absolutely correct picture. In other words, you can reproduce and analyze SRC phenomenology in a low resolution picture, just as you can do nuclear structure calculations in extremely hard to do one or the other, but the point is you can do it. The other thing that, well, had I had more time to show my deuteron electrodisintegration, I would have convinced you that physical interpretations vary with resolution scale. as do practical things like final state interactions and overall ease of calculations. And the question I'd like to ask is, can we somehow exploit this? Another thing, connecting more to conventional low energy nuclear physics. Can we use these RG methods, for example, to connect spectroscopic factors, which are inferred in a low resolution shell model picture? Can we connect that with SRCs in a high resolution picture? This is an ongoing issue in nuclear structure. Structure is always treated in a low resolution shell model-ish type picture, whereas the reaction theory is treated in a single particle, which is, single particle probe, which is implicitly a high resolution picture. And so is that mismatch making things difficult? And then lastly, can we use these simpler low resolution scale wave functions together with these very nice simplifications of factorization that come from the operator product expansion and these RG transformations? Can we do that to actually help out SRC physicists? Namely, can we leverage the simpler many body calculations together with the fact that all the interesting Q dependence is absorbed into a few body Wilson coefficient, which doesn't care about the many body calculation? Can we do that to be able to push calculations that would be of interest to them to describe hard electron scattering in heavier nuclei? And with that, I will end. Thank you.
Thank you for the very interesting talk. Are there any questions? Vladimir?
May I ask a question?
Yeah,
sure.
What are, if any, observable effects of short-range correlations in the region of low energy up to, let's say, astrophysical processes or up to giant resonances? In this region, what would be the observable effects?
Well, you would, let me put it this way. You would observe their effects if you're doing your calculations in a low resolution framework, if you don't consistently encode the effects on general operators. So I think that's part of the disconnect between the two fields, is that I think that some of the statements that have appeared over the years that low energy nuclear physics is missing this SRC physics and so is therefore wrong is really based on the fact that calculations have not always been done consistently, where you need to not only evolve your Hamiltonian, but you need to evolve your probes and everything that would come in to describe a reaction.
Are there any critical phenomena? If you observe them, you say those are effects of short-range correlations at low energies. Can you indicate something like that?
Well, sure. I mean, it's the whole NP dominant stuff, I would say. But that's just tensor force physics. And if you're working in a modern Ab-initio framework, you have that. So there have been, there is speculation in the SRC community that, understanding the SRC pairs, which can be viewed as like a instantaneous local fluctuation to high density, that maybe that can be of relevance for understanding high density neutron and nuclear matter. I'm not entirely sure if I get that connection, to be honest. But because I think you know, in a SRC you have a high a momentary fluctuation due to high density, you know, for these pairs, a high local density, but those are highly you know, highly virtual off-shell phenomena, and so I'm not sure how that connects with high density, you know, equation of state, where it's more like you know, understanding things like on-shell, you know, quasi-particle physics and stuff like that. So yeah, I don't know. I think that remains to be seen.
Thank you.
Yeah, or you have your hand raised.
Can you hear me?
Yeah. Yep.
Excellent. Great. Thank you. It was really nice. I wanted to follow up on your second to last point, right, about extending the reach of low resolution theories. Do you have any ideas on the more, say, what is an appropriate way of thinking about incorporating high Q SRC effects to things like DFTs? I mean, I've seen a few papers by a few groups on the archive recently discussing about the impacts of SRCs on cooling rates of neutron stars. There's a paper by a Chinese group talking about the stability of certain neutron stars, and it all really depends strongly on how you introduce these effects to, in that case, maybe a relativistic mean field theory or a DFT. Do you have any thoughts about the proper ways to do that? I'm not sure it's done properly, to say the least.
Yeah, no, I have vague thoughts. So the point is, I mean, if I mean, you want to use these high Q measurements, which actually, you know, learn something new about the nuclear force that we don't already know. So in that sense, that's why I think, you know, viewing like the inclusive ratios, to me, that's vaguely disappointing, because you see that you get things that are the same no matter what you use, and so you really haven't learned anything. Whereas if you're looking at more exclusive processes, where, from what I understand, you know, from talking to you and others, that there you can see some noticeable discrepancies depending on the nuclear force model that you're using. So assuming that you can extract some you know, meaningful difference where different models behave differently, then the point is, I think, you know, if this is a high Q phenomena, you can you know, parameterize that physics some way, and then think of doing RG down and using this factorization that, you know, whatever new high Q physics you parameterize will all ultimately get absorbed into one of these factorized Wilson coefficients. And so then if you wanted to use that information in an actual you know, nuclear structure calculation, you could still proceed using your comfortable low resolution Hamiltonians with operators that have been suitably corrected. But in order to make use of this, you have to, from the high Q experiments, you have to be able to infer or construct you know, a high resolution model that has that new physics in, that I can then take and RG it down. I don't know if that makes
I'll
sense.
just make two very brief comments and finish. One is, even in the high resolution picture, we see struggles understanding the E prime scaling plateaus on a quantitative level. There's just yesterday a PhysRevC letters out on this by Ronen and my students and others. So I think we are struggling to find also even in high resolution, the connections to better than 10%-ish accuracy on those observables. The other thing I just want to kind of bring out, because people are working on calculations, so it's important to know what data is coming. There is a new series of inverse kinematics measurements for SRCs with hadronic probes The first result is going to be published in Nature Physics, I guess, in the coming weeks. We already did the proofs from an experiment we did with carbon from Dubna. And then there's follow-up measurements later this year, and with the carbon-16 beams and carbon-12, of course, but mainly carbon-16 in R3b and GSI. So there is going to come quite a lot of data that will also relate things to the different low-energy nuclear structure effects by doing gamma coincidences, by looking at breakup to an A-2 system, alphas, if you're talking about carbon coming from the P shell, coming from the S shell. So there will be more and more observables that try to dissect the connection to the lower energy nuclear structure while doing this, so kind of measurement at 4 different scales in a sense. And it would be good that when this data comes out, we have more discussions on how we can do this theory properly, because that has to connect the low energy, the low resolution theory with the high resolution theory as well for the IQ. So it can be very interesting to understand those. Thank you very much.
Yeah, thanks.
Yeah,
That's interesting.
Pavel, you're next.
So if you try to calculate high momentum tails with Green's functions, then you get sort of characteristic fall off of momentum tails like 1 over square of kinetic energy. That could be then moderated maybe by some softness of the interactions. Is that kind of, so it would give a region of momenta where it goes like 1 over momentum to the force. Is there a similar picture or simplified picture emerging in the matrix elements that you wrote down?
Yeah, so if I think I know what you're asking. So if I look like at, where is it? Yeah, so if I look at this, damn it, it's, okay, I'll try not to touch anything. All right, yeah, so if you look at this expression that we derive, using these RG arguments, this gamma function, which carries all the Q dependence, is entirely specified by matrix elements at the 2-body level. And you can analyze that goes kind of to leading order. It goes like V of Q over Q squared. And so you square that, you get the 1 over Q4 with some moderating factor up.
Okay, great, thanks.
Okay, Elena, you're next.
Hi, Scott. Thanks for a very good talk. I had a question regarding your first highlight, namely that RG smoothly connects high and low resolution pictures. So seemingly, the short-range correlations should somehow be related to the internal nucleon structure. So I was wondering, is this information incorporated in some way in the theory, or maybe on the other hand, it can be extracted from calculations?
I'm not, so are you referring to this this kind of empirical observation that the magnitude of the EMC effect, which is a modification of the nucleon structure in medium, is correlated with the size of the SRC?
For instance, yeah.
Yeah, so that, so again, I don't have the plot here, but you've probably seen it where you see this beautiful linear correlation between those two seemingly unrelated quantities. And I would argue that again is in a EFT RG language is easily understood just using these OPE type arguments. And in fact, that has been done by some nice papers by originally, and then there have been more recent ones kind of following that up. But that explains or suggests an explanation as to why those two quantities are are connected. Yeah.
Okay, thank you.
And Dick.
Hi, I just wanted to maybe reemphasize some things that Scott said in connection with Orr's question, for example, about adding to other theories and stuff. So the key thing on this is we describe this stuff as short-range correlation physics. So there's lots of short-range physics, and it gets incorporated in the theory just in different ways. So it doesn't appear in the wave functions. We do not have short-range correlations at short distances, I mean at low resolution, but it's there in the operators, and it's there in the Hamiltonian as one of the operators. So it's already there in Hamiltonian. But you have to keep in mind then, if you're going to do other things with the result of your Hamiltonian, then things that you thought were simple operators may not be simple operators anymore. So you have to have two-body contributions to things that you thought were only one body before. And as Scott has emphasized with this factorization, that actually doesn't make things harder, makes some things simpler. And because you can figure out these operators from relatively simple calculations rather than big many-body calculations where you would have to deal with if you put them into the wave functions. Okay, so I just wanted to emphasize that point there. Thanks.